Good morning. Myself, Professor T. N. Oza here. Today, I am going to present to you a new video. The title is The Schrodinger Wave Equation. As you all are aware, this is an epoch-making discovery done in 1926 by Erwin Schrodinger. This equation finds use in almost all branches of chemistry, physics, mathematics, and also in some social sciences. I have found people using this equation. So today we will discuss about this equation point-wise. For simplicity, we will discuss it under the following points: introduction, Erwin Schrodinger's wave equation, stationary wave equation, separation of variables, GT as a sine wave function, obtaining the eigenequation, introducing de Broglie equation, acceptable wave function, orthonormal, orthogonal, and normalized eigenfunctions, statistical interpretation of wave function psi, comparison with Bohr's model, and lastly about Erwin Schrodinger himself. So let us discuss point-wise. Introduction. As a fallout of black body radiation experiment, photoelectric effect, and Bohr model of atom, since around 1900, it was felt by a few celebrated physicists that apart from the Newtonian mechanics prevalent at that time, something called new physics had to be conceived. 1924, Broglie gave his famous equation connecting together the wave nature defined by wavelength lambda and particle nature defined by mass m and velocity u or momentum say along x coordinate. For a moving teeny particle such as electron, atom or molecule, the equation is wavelength lambda equal to h over p is momentum, lambda equal to h upon m u, where u is velocity. This is equation 1. Erwin Schrodinger's wave equation. Erwin Schrodinger in 1926 developed a new equation called wave equation to describe the behavior of very small particles like electrons, atoms, molecules. He had used the stationary wave equation, equation number 2 noted below, and clubbed it with the de Broglie equation, equation 1 noted earlier, to find a second order time independent differential equation in which discrete electron energy orbits proposed by Niels Bohr in 1913 in the form of his second postulate, that is angular momentum m equal to nh upon 2 pi by n integer, was replaced by a mathematical probability function, wave function psi. Thus, the concept of discrete energy orbits as proposed by Niels Bohr was replaced by a definite 3D space or energy orbital. This conforms to the Heisenberg uncertainty principle. The so-named electron energy orbitals represent the three-dimensional space around the atomic nucleus in which there is maximum probability of finding an electron. So this was a radical change from orbit to orbital. The stationary wave equation, equation number 2, shown below, d2i upon dx2 equal to 1 upon u square plus d2i upon dt2. Here u is the velocity of the particle, y is the amplitude or a wave function, x and t are variables. X is position variable, t is time variable. The vibrational frequency of and wavelength lambda are also related to velocity, u equal to lambda into frequency. And the wave is stationary wave because it is like a string fastened at both ends. Therefore, at both ends, amplitude goes zero. The maximum value of amplitude of the vibrating spring is assigned a symbol A. Actually, A will be a constant. So at any time t, the amplitude y depends on two variables, x and t. This is very important to remember. At any time t, the amplitude y depends on two variables, x equal x and t. Separation of variables. Because here the amplitude depends on two variables. So in order to be able to solve the equation, we need to separate the variables. So we can write y equal to fx gt. These two are functions. The function fx depends on position x only, not t. Likewise, the function gt depends on time t only, not position x. So both are independent. gt as a sine wave function. From classical physics, we know that function gt can be written as a sine wave function or a cosine wave function. Gt equal to y maximum sine 2 by ft. Putting y maximum as a becomes a sine 2 pi ft. Frequency a is speed upon wavelength. Therefore, we can write amplitude y equal to fx gt, replacing gt by a sine 2 pi ft. Y becomes fx a sine 2 pi ft. Question number 5. Obtaining the eigenequation. In order to obtain an eigenequation, equation 5 can be differentiated keeping fx constant, gt as variable. Next time, doing the reverse, gt as constant, fx as variable. So differentiation with respect to t gives dy by dt equal to 2 pi f a cos 2 pi ft dot fx because fx is constant. Differentiating again, we get d2i upon dt square equal to minus 4 pi square f square a sine 2 pi f fx. So this is our eigen equation because on both sides we have the same wave function. Similarly, differentiation of equation 5 with respect to x while keeping gt constant yields d2i upon dx2 equal to gt d2f dx2, equation 7. Now, what we will do, we will consider equation 2, equation 6 and equation 7 together. What we will do, we will substitute the relevant values from equation 6 and equation 7 into equation 2. So equation 2 is, again for simplicity, we are reproducing here d2i upon dx2 equal to 1 upon u square multiplied by d2i upon dt square. This is equation 2. So the term on left hand side, d2i upon dx2 is equal to gt d2f dx2, and the term on the extreme right hand side, d2i upon dt2 is equal to minus 4 pi square f square gt of x. So we will simply substitute the values to get gt d2 of x dx square equal to minus 4 pi square f square 1 f square lambda square multiplied by gt and again multiplied by fx. Cancelling gt from both sides and cancelling f square from denominator and numerator, we are left with d2f upon dx2 equal to minus 4 pi square lambda square minus 4 pi square over lambda square multiplied by fx. This is equation number 9. Now At this point, we will introduce de Broglie equation in equation number 9, get the wave mechanical equation. And we know the Broglie equation says 1 over lambda square equal to m square u square upon h square. Transposing m square u square can be written as 2m into m u square r over 2 kinetic energy. So that is how we say 1 upon lambda square is equal to 2m multiplied by E minus V over h square, where E is total energy of the system, V is potential energy. So I repeat, 1 upon lambda square becomes equal to 2m, m is mass, multiplied by E minus V over h square. We will simply substitute this value in equation 9 to get d2f upon dx2 equal to minus 4 pi square fx into 2m e minus v upon h square. Collecting 2m and 4 pi square together, it becomes minus 8 square m upon h square e minus v fx. Here I would like to remind you one point. Sometimes the books mention h square upon 2m. That is simply using the modified Planck constant h upon 2 pi equal to h cross. So remember, this equation can also be written as minus h square upon 2m e minus v fx. So again transposing it, it becomes d2f upon dx square plus 8 pi square m upon h square e minus v fx equal to 0, equation 13. Very important equation. Equation 13 is valid for the propagation of particle wave along x coordinate. Equivalent equations can be written for the wave motion along y coordinate, along z coordinate. Taking sum of these three and replacing the function fx by the more popular function psi xyz, we can write the time-independent Schrodinger wave equation in 3 dimensions as d2 psi upon dx2 plus d2 psi upon dy2 plus d2 psi upon dz2 plus 8 pi square m upon h square e minus v psi equal to 0. Again simplifying it, we can use Laplace operator in place of d2 upon dx2 plus d2 upon dy2 plus d2 upon dz. A scalar operator. So the equation becomes L square psi plus 8 pi square m upon h square e minus psi equal to 0. We can multiply this whole by minus h square upon 8 pi square m to get minus h square 8 pi square m del square plus v whole multiplied by psi equal to v psi. More simplified form is h psi equal to v psi, where h is called Hamiltonian operator. It consists of two parts, kinetic energy operator T and potential energy operator V. So in this manner, we have derived Schrodinger wave equation in a very simple and logical manner. Remember, this equation is for those particles which have dual behavior, particle nature as well as wave nature. Also, this equation can be applied to those systems which only show particle nature, not wave nature. That is the beauty of this equation. And this equation is most celebrated equation of quantum mechanics. Actually, it forms the heart of quantum mechanics. So I hope by reading this video 2-3 times and writing various equations, unless you write the equations, you cannot remember them. So please write the equations, learn each and every term by heart, and you can master over it. A little bit about acceptable wave functions. Solution of Schrodinger wave equation yields the state function or wave function psi. All values of psi are not acceptable. Only those values of wave function psi are acceptable which fulfill certain conditions. They must be single valued at all points along x, y, or z coordinate. They must be continuous and finite. That is to say, for the wave function psi to be acceptable, it must vanish at infinity. Also, the acceptable solutions of Schrodinger wave equations should be mutually orthogonal and individually normalized. So, only those wave functions are acceptable which meet out these conditions. Orthonormal, orthogonal, and normalized eigenfunction. The wave function is said to form an orthonormal set according to the following condition: integral psi star n psi m dv 0 where n is not equal to m or 1 where n is equal to m. They are said to form an orthogonal set if the integral vanishes, that becomes 0, and normalized set if it is unity. Orthogonal psi star n psi m dv equal to 0. Normalized psi star n psi m dv integral 1. Statistical interpretation of wave function psi. Max Born had suggested the wave function psi is a probability amplitude function. Thus, we can define the probability of finding the particle, say within the range x and x plus dx, by the following equation: px dx equal to psi x star psi x dx equal to mod psi x square dx. The symbol two lines, vertical lines, represent mod. In this, psi star is the complex conjugate of psi. Px dx is the probability and px is the probability density. Thus, integration between limits minus to plus infinity px dx equal to integration between the sum limits psi x star psi x dx, or we can say psi x square dx equal to 1. For motion along x, y, z coordinate, px dx is replaced by pr d3r. R is position coordinate representing x, y, z coordinates, and integration of psi r star psi r d3r, alternatively psi r square d3r equal to 1. The integration is carried over all space, that is d3r equal to dx into dy into dz equal to v, v for volume. Comparison with Bohr's model. In Bohr's model of atom, electron is assigned to a circular path at definite separation from the atomic nucleus. Although in the Born model, question for calculating the exact energy of electron has been derived. The location of electron is in orbitals, the 3D space around the nucleus, where the probability of finding the electron is maximum. Thus, there always exists uncertainty regarding the exact position of the electron. Thus, this treatment is in conformity with the Heisenberg's uncertainty principle. About the celebrated scientist Erwin Schrodinger himself, his full name Erwin Rudolf Joseph Alexander Schrodinger. He was born in 1887, August 12, lived up to 1961, 4th January. He was an Austrian Irish physicist, Nobel laureate of 1933. He studied at the University of Vienna and is famous for his contribution to quantum mechanics. Thank you very much. I hope you will realize the importance of this equation and you will understand it, not only from examination point of view. If you are going to graduate in chemistry, you should know about Schrodinger equation very well. Thank you very much.